Hello again. We've been talking about scaling laws, and today we're going to focus on the scaling laws for heat transfer. That is, how things heat up and cool down, and how that's related to their size. It sounds like a kind of dry topic, so we're going to focus on two examples as we work through this, because it is actually important. The first will just be a cooling problem. How does the rate at which something cools down depend on its size? And the other will be an application called thermal therapy, which is a method of treating disease like cancer by using magnetic nanoparticles. Okay, so hang on and we'll get started. Very good. As I mentioned, we've been talking about scaling laws. We defined what a scaling law is and talked about the characteristic dimension. And then we talked about how scaling laws can determine how strong something is, and really what strength means for a material. And to do that, we talked about stress and strain, and apply these to talk about strength. And we found that in one reckoning of strength, how capable is an object of supporting its own weight, that small means strong. The smaller we make an object, the stronger it is. Today, we're going to talk about heating and cooling. How these scale with an object size. We're going to apply this to two problems. What I'll call the cooling cup or cooling object. How quickly does a cup of coffee cool off? And does it matter if it's a big cup of coffee or a small cup of coffee? And then, as I mentioned, I want to apply this to an application to an application called thermal therapy, which should be interesting too. Okay, that is what we're going to get started with. All right, so let's start with this important problem. Which cup of tea cools faster? Here are two cups, a large cup, a small cup. Which do you think will cool off faster? Well, that's the problem we're going to address. Although we'll look at it in this simplified form. Imagine I have an object that's immersed in some kind of medium. And the object is hot, and it's going to cool off by transferring heat to the medium. Okay? And here, the object is a cup of tea, and the medium is the air or the table or whatever. But in our problem, we'll imagine the medium to be kind of homogeneous, all the same substance. And we'll ask, how does the cooling rate depend on the size of the object, on the characteristic dimension, which might be its diameter, as shown here? Now, you've probably guessed what the answer is from life experience. And if you haven't, you might remember that Feynman made an enigmatic phrase. He said about nanomachines, they won't run hot because the heat escapes from very small devices very, very rapidly. It's kind of giving it away a little bit, but let's see how it works. So hang on one more moment and we'll get started. All right, so let's address the scaling rate for cooling. We're going to start with some definitions. So some things we need to find are the temperature, T, probably familiar with this. In our discussions, the temperature will usually be in degrees Kelvin, where the temperature in Kelvin is just equal to the temperature in centigrade minus 273.15. The next thing we need is the heat capacity. The heat capacity tells how much heat energy I have to add to raise the temperature of an object by 1 degree Kelvin, okay? And so it has units of joules per degree Kelvin, naturally enough, okay? The second thing, or the third thing rather, is a related quantity called the specific heat. And in this case, the specific heat per unit mass. And what the specific heat tells us is the amount of energy I have to add to raise the temperature of 1 kilogram of the substance by 1 degree. So it has units of joules per Kelvin per kilogram. Not surprising, right? You may have encountered this previously, and you might have seen other versions like the molar specific heat or the specific heat per cubic centimeter or something like that. But we'll use the specific heat per unit mass. We're going to use Q here to denote energy. And specifically here, I mean heat. Heat is a form of energy. So this has the same units as energy, joules. But heat, if you like, is the most disorganized possible form of energy in any system. I'd like to tell you exactly what I mean by that in a clear and concise way, but to do that, you'd have to take our statistical mechanics or thermodynamics class. For the moment, Q is heat, and heat is a form of energy, and we measure it in joules. All right? And then we can change the amount of heat in a substance. We can change the amount of energy in a substance by having it absorb power or by having power energy being transferred away as a flow of heat. And so for this discussion, we'll need to talk about, got the wrong one. We'll need to talk about heat flow, PT. And the heat flow has units of joules per second. So that makes it a power. Joules per second is also the same thing as watt. So these are the quantities we need to understand just right at the moment. And we also need some relationships that relate these quantities together. And let's just take a look at that. A couple of these will be very familiar or not too surprising. And one is probably going to be new. So first, the heat capacity is related to the specific heat. It's just the specific heat per unit mass times the mass. And so it's the specific heat per unit mass times the density of the object times its volume, okay? So it's worth noting here that the heat capacity of an object is proportional to its volume. The second thing we want to say expresses energy conservation. It tells me that if the only way that the amount of thermal energy or energy of an object can change is if heat is either emitted or absorbed. And to start it with our cooling problem, we'll just have heat emitted. We won't worry about heat being absorbed. And that means that the rate of change of the energy with respect to time, okay, will be equal to minus the thermal power coming from the object, okay? Notice these both have the same units, joules per unit time, or watts, And it makes sense. If power is flowing out of an object, then the object is going to be, then the heat in the object is going to be getting smaller. Okay? So this expresses energy conservation. If power flows out of the object, the amount of energy in the object must be getting smaller. And the last one is called Fick's law. And it's probably unfamiliar. Fick's law tells me that the thermal power from an object in watts is equal to the following: minus kappa times A times dt dx. Here, kappa is called the thermal conductivity. And A is the surface area. And dx dt tells me the rate of change of the temperature with position. And sometimes it's called the thermal gradient. And basically, the fact that the power is proportional to the thermal gradient tells me that if I have a large temperature difference between 2 points, then there'll be a lot of heat flowing through it from the hot area to this cool area. Okay? I'm going to illustrate this last law with a drawing. Give me a second and don't laugh. So let's imagine that we have our hot object over here, and then it's going to heat is going to transfer from the hot object into the surrounding medium. There we are. The transfer of heat, that's PT. The area is just the surface area of this wall in this drawing. And then the thermal gradient is just the temperature difference between 2 points that are close together. So if these have temperatures T1 and T2 and positions x1 and x2, then dt dx is just equal to the ratio of T2 minus T1, the change in temperature, divided by x2 minus x1, the change in position. And strictly speaking, it's equal to this in the limit that dx is very small. Okay? And finally, the thermal conductivity here is the thermal conductivity of the surrounding medium. Okay? Very good. So we have these definitions. They're all pretty straightforward. We have these relationships, 2 of which are straightforward, and then the last one is probably a little bit of a stretch. Luckily, for the cooling problem, we don't need to look too hard at these relationships, okay? We only need to remember that the heat capacity is proportional to volume, and note that this third law says that the heat flow, PT, is proportional to area. Okay, I'll leave that up. And then remember, our problem looks like this. We have our hot object that's immersed in some kind of fluid or medium. And heat is flowing out from the hot object. And this has some characteristic size, our object does, d. Okay. Well, very good. So now we're ready to answer our first question. What's the scaling law for the cooling rate? Or do small objects cool faster than large objects? Okay. Well, to begin with, let's start with this law, the energy conservation law, dq dt is equal to minus pt. Okay? Since the notion of heat capacity tells me that a change in the energy means a change in the temperature for my object, that is, we can say that dq dt is equal to the heat capacity times the rate of change of the temperature with time. Okay? Of course, that's the thing that we're the most interested in. The rate of change of temperature with time, the cooling rate then, is equal to minus Pt divided by the heat capacity. Okay? And now we can immediately write down the scaling law because we know that that Pt, the thermal power emitted by my object, that's proportional to the surface area. Whereas the heat capacity is proportional to the volume. Okay? The area goes like d squared. The volume goes like d cubed. And so the cooling rate goes like 1 over d. So the smaller d is, the larger the cooling rate will be. And so small objects cool faster. Okay, here, let's pause here.